Hey, we're back. This is a video solution to problem 9 from Superquiz 2. And here we're doing a little bit of modular arithmetic. My favorite. So here, hey, this is pretty nice. We're working modulo 5. And oh my goodness, 4,298 to the 2,874th power. I don't want to do that by hand. Oh, thank goodness we're working modulo 5. Oh, and I missed it. There's a plus 374 to the 12th. But again, thank you. We're working modulo 5. Okay, so what do we need to remember here? First, if I'm working modulo anything, if I'm working a sum, I can do the sum individually. And if I have a product, I can do the factors individually, right? So what I mean to say is, if I'm taking the equivalence class of a sum, that's the same thing as the sum of the equivalence classes. All right, modulo whatever, all right? And if I have the class of a product, that will be the product of the classes. Okay, so this tells me all I need to do is actually work out what is the residue, what are the residues for 4,298 and for 374. And then I'll have a smaller problem, all right? So 4,298. Well, mod 5 is pretty easy, right? 5 goes into 10 twice, so I can just subtract any multiple of 10 I like. So I can subtract 4,290 from this, and then I'll be left with 8. And then I can subtract another 5, and I'll be down to 3. So modulo 5, 4,298 is just 3. All right. So the side calculation, right? 4,298 subtracting 4,290, which is a multiple of 5. Right? You can always subtract multiples of your modulus, is equal to 8, and 8 minus 5 is equal to 3. So that's where I got that. Okay, now, if I want to raise this to the 2,874th power, you might be tempted to start asking what is 2,874 modulo 5. Don't do it. Okay, this is not a correct approach. We do not have a formula that says you can reduce the exponent modulo 5. Right? All we know is that I have 4,298 to the 2,874, which means I have 2,874 copies of 4,298 multiplied together. But modulo 5, each one of those is 3. And so 4,298 to the 2,874th power is congruent modulo 5 to 3 to the 2,874th power. Well, that still seems horrible to compute, right? That's an absurdly big number. So let's compute just a few examples and see what's happening. So if I raise 3 to the kth power, when k is 1, I get 3. When k is 2, and of course this is all going to be modulo 5. When k is 2, I get 9, but mod 5, I get 4. Okay, so I'll write here first. This was 9, but this is congruent to 4. Now to get the third power, I could go right to 27, or I could just multiply by 4 and get 12. Either way, all right, modulo 5, I'm going to get 2. 27 mod 5 is 2, 12 mod 5 is 2. Okay, fourth power. Well, I just multiply 2 by 3, I get a 6, which mod 5 is 1. And I'm always happy to see a 1 because it means I'm going to start repeating the pattern. So when I get to a 5 now, I do 1 times 3. Hey, that's 3 again. And it's just going to keep cycling through. A 6 would, the 6th power will give me a 4. The 7th power will give me a 2. The 8th power a 1, and it'll keep cycling. And so you see what I get, modulo 5 is just a pattern here, right? Every 4, it's going to repeat. So all I need to know is actually what is 2,874 modulo 4? Huh, who would have thunk it? 2,874 modulo 4. Well, the great thing about doing modulo 4, right, I can subtract as many copies of 4 as I want. And because 4 goes into 100, I can immediately just subtract 2800 from this. So that's going to be congruent to 74. Now I happen to know 4 is going to go into 72. If I didn't know that, well, let's see. I could get rid of, say, 40, and I'm left with 34. Get rid of 32. Now I'm left with 2. So modulo 4, this is 2. So raising 3 to the 2,874th power is going to be the same as if I'd raised 3 to the second power, which means I'm going to get this congruent modulo 5 to 4. All right, so I get a 4 right here. Now, I still have to do this 374 to the 12th. Well, we're going to proceed in the same way. 374 modulo 5. It's easy enough. I can get rid of 370, and I'm just left with a 4. And now I need to take 4 and raise that to the 12th power, modulo 5. So let's start looking at that. So 4 to the k. Okay, and what k? So when k is 1, we get 4. If I square 4, I'm going to get 16. But 16 is congruent modulo 5 to 1. Oh, wow. This is just going to alternate 4, 1, 4, 1, 4, 1. Okay, so it's going to be a 1 on the evens and a 4 on the odds. Well, let's see. We're raising it to the 12th power, right? So 374 to the 12th is congruent to 4 to the 12th, and even power is a 1. So this is actually just congruent to 1 modulo 5. And so we come back up. This is a 1. 4 plus 1 is going to be 5, but 5 is 0 modulo 5. All right. And you said, well, this was the least positive. Is 0 positive? Well, no. But you remember we had this little terminology problem. All right. This goes back to Gauss and his Disquestiones Arithmeticae. He describes the least positive residue set as including the 0, right? So it's a little abuse of the language. But we are going to forgive Gauss because he's Gauss. Okay, well, that's how we can do some modular arithmetic. Please don't make this mistake, and we'll see you next time.